Okay, hi everyone. Welcome to the second day. So this morning session will have a series of short science talks. And the plan is to have 15 minutes per talk. So for the speakers, I will give you a 5-minute warning after 10 minutes. So we can leave some time for questions. That would be great. Another announcement, our email is down, so the email that you would send to the local organising committee doesn't seem to be working at the moment. So if you need to get us, please contact us on Slack instead, or some other way. Okay, so to start us off, Andrew will be talking about the effect of a constant velocity of the source on gravitational waves. So take it away, please.
Hello, everyone. First of all, thanks for the invitation or the chance of giving this talk. My name is Alejandro. I'm a postdoc at the Tianjin Center in Zhuhai in the south of China. And today I'm going to talk about the effect of a constant velocity of the source on gravitational waves. This is a topic I've been working on now for several years since my PhD. And today I'm going to give, let's say, a summary of my current understanding and of my most recent results. Okay, let's start first with the motivation. Why do I care about velocity, or why in general should we care about velocity? The point is that traditionally, let's say, gravitational wave sources were described in a very simple way. We assumed they are like some isolated system which is evolving due to the emission of gravitational waves, and we detect them. But nowadays, we know this is very simplified. If you look, for example, which other talks are going to come, many people are now starting to realize or working harder on describing that gravitational waves are actually embedded in some environment. These environments are usually very dense because we need them to be dense from the start in order to produce a binary which then emit gravitational waves. So we can have their gas, there are some other stars or compact objects interacting with our binary. In particular, this could be the supermassive black hole in the center of the galaxy. And also the host system itself can be interacting. For example, galaxies are often in galaxy clusters which interact with other galaxies. And although many of these effects can have, or many of these environmental effects can lead to different effects on the gravitational wave, one thing that they tend to have in common is that they cause a motion of the center of mass of the source due to gravitational pooling, due to dragging of the gas, and so on. So motion is actually quite important for us and should be considered for two reasons. One is, if we really want to have accurate waveform models, basically going back to this idea of a very idealized source where we really can understand the underlying physics, we need first to have an understanding of all the environmental effects so that we can clean them out and perform accurate measurement of the gravitational waves. The other idea is that we actually want to use gravitational waves to also perform astronomy, to really understand the environment, the interaction, where the sources come from, where they go, so on and so on. And for that, we need a clear understanding of the effects so that we can include them in our waveforms to have an interpretation of them. The question, of course, is how relevant these effects are, which usually is measured like by how strong or the magnitude of the effect. And for velocity, there are two kinds of effects that I think stand out. One is the peculiar velocity of galaxies. As I said, sources of gravitational wave usually will be in some host system, a host galaxy, because these are just like the most dense environments we have. And galaxies themselves are usually embedded in groups or galaxy clusters, which lead to an interaction of a mutual interaction of all galaxies and an acceleration, and at the end, a motion of the galaxy, which then just pulls the source with it and makes it move. This motion, the specular velocity of galaxies has been measured with light to a certain extent. And there we see that the average velocity is around 1,000 kilometers per second. The first time I heard this, I was actually quite surprised because, I mean, galaxies are very huge. You don't expect them necessarily to be moving fast, but 1,000 kilometers per second is a very high velocity. And current measurements show that they even can go up to 2,000 kilometers per second or a bit more than 2,000 kilometers per second. On top of that, our current observations by light are quite restricted, but it looks like that when we go further back in time, so to higher redshift, these velocities even could increase more. So we could have even velocities above 2,000 kilometers, maybe 3,000 or more. So this makes it very interesting because these are very high velocities, but at the same time, they're acting on almost all sources because basically all sources of gravitational waves are somehow embedded in a galaxy. The other kind of velocity of interaction, which I think is very interesting, are triples. Many people are studying triples because when you have a binary or you have a system which is dense enough to get a binary, it's not very difficult to then get a triple. And the triples will basically cause an orbital motion of our gravitational wave source. And these velocities can start with just a few hundred kilometers per second, which still would be quite high, but even can go up to highly relativistic velocities, in particular if the binary is circling a supermassive black hole, where you can easily get velocities of several percent the speed of light or even 10 or 20, just if it gets close enough. Okay. So we know that the velocity is there, and the question is then, how does velocity really affect gravitational waves? This luckily can be described or can be divided in a simple way, namely that we know the gravitational waves, or I have been working on this and I have been understanding that this can be divided in three kinds of effects on a wave induced by a Lorentz transformation. First is the Doppler shift. The Doppler shift causes that the frequency changes, so velocity, gravitational waves which are emitted opposite to the line of sight get redshifted, and along the velocity, they get blue shifted, which simply speaking change the frequency of the wave. On top of that, there is also a change in the apparent magnitude of the source, so that this translates into a change of the luminosity distance. So these two are part of the Doppler shift, and this is what is usually included when people want to consider velocity. And these are also two forms that appear for cosmological expansion. But for velocity, we have also other things. There is also aberration. Aberration is making that the rays emitted by the gravitational waves are shifted towards the direction of the velocity. This then leads to two different effects on the wave. One is a change of the orientation of the rays relative to the, let's say, coordinate system or the preferred direction of the source, for example, compared to the angular momentum of the source, which changes our perceived inclination and so on, and depends also on the velocity perpendicular to the line of sight. I will not go deep into this, but I will explain a bit later why this part is important. Maybe more important, at least for first consideration, is that aberration also changes the amount of radiation emitted into a certain direction. So there is more radiation emitted towards the direction of the velocity, and therefore the intensity of the field changes in a direction-dependent manner, again with some factor which is proportional to the Doppler shift. Last, there is the polarization rotation. Gravitational waves have preferred directions of oscillation. For example, for plus polarization, this is like the two direction in which the plus polarization is the strongest. And this one gets rotated in the plane of the polarization when the source is moving. So taking these three effects together, we can then describe how the gravitational wave seen by this observer, here we're looking on the complex amplitude, so the combination of the plus and the cross polarization in the observer frame depends on the gravitational waves in the source frame, or the complex amplitude in the source frame. So as I mentioned first, we have here this polarization rotation. This from an observational point of view is important because the plus polarization, for example, seen in the observer frame, is then a mixing of the plus and cross polarization in the source frame. And we know that, for example, we want to use the ratio of plus and cross polarization to break the inclination distance degeneracy, but this mixing comes in. So this would be, for example, one example of why we should consider velocity if we want to have accurate measurements. Then second, we have this combination of the change of the apparent amplitude due to aberration and due to Doppler shift. But they enter with different factors. So one is this transformation basically times d, and this in divided d square. So what actually happens is that when the source is moving and it is redshifted, it appears to be closer. This is in stark contrast to cosmological redshift, where redshifted sources appear to be further away, which also shows that gravitational waves are affected by a velocity in a different way than cosmological redshift. Also, traditionally, people tend to treat them in the same way. Then last but not least, there is this change of the frequency, which is a change not simply of the frequencies. From my current understanding, that's a change of the fundamental frequencies. But gravitational waves usually have several modes, and the modes have a frequency which is a multiple of a fundamental frequency. So actually, this change of the frequency leads to more complicated and sometimes even time-dependent patterns on the frequency that we are seeing just due to the velocity. And it's not just this simple constant redshift, which is usually assumed when describing, which I think just stems from the fact that we tend to consider only the dominant quadrupolar mode. So then what I've been doing recently together with it.
5 minutes left. Sorry.
Okay, yes. Together with a student here at the Tianjin Center, Tianjin Ye, he has produced this plot, so credits go to him. We have started looking into an example. The example is a standard Emery. By standard Emery, I mean Emery with a supermassive black hole of 10 to the 6, a small black hole of 10 solar masses, circular orbit, 1 year before plunging. And we put this Emery at a distance of around 0.1 parsec, which corresponds to the distance of around the gamma cluster. So this is a distance which is definitely another cluster, which we wanted to have because of the peculiar velocity of the clusters. And this also corresponds to then having a source with an SNR of 200. So it's loud, but not extremely loud. Like it's above the usual detection threshold, but nothing extraordinary, let's say. And for this source, we studied how well we can detect the velocity, as well as the impact of the velocity on certain parameters. First, looking on how well the velocity can be detected, one thing is the magnitude. And this is a Fisher matrix analysis, so it's a bit idealistic, but it shows that for velocities of 2000 or 3000, this should also apply for lower velocities. The magnitude is actually the accuracy of the velocity magnitude is extremely good, only 2 kilometers per second. And even if like the reality would turn out to be a factor of 10 worse, we still would be with 20 kilometers per second, which is really good. Then also the direction can be measured. As I mentioned, there is this dependence on the perpendicular direction of the velocity, perpendicular to the line of sight. So this is interesting because with light, we only can measure the velocity along the line of sight. And also the detection accuracy is not very good. It's around 1 radian. It's still providing information we only could get with gravitational waves and not with light, which I think it makes it very interesting. And then last but not least, as I mentioned, the detection of other parameters, which are in principle independent of the light, of the velocity, can be impacted by a motion. So if you really want to conduct accurate studies, you can see by this plot that at least for some of the parameters, you definitely need to take into account velocity. For example, here the mass is changed by some factors, but also the distance and the inclination are affected by them. So you should consider this to have good templates. Okay, so yes, that's all. Thank you very much.
Thank you. We do have time for questions. So we have a question. Would you like to come close to the mic, please? Question from the room.
Hello, can you hear me? Yes.
Yes.
Thank you for your talk. Just regarding your last slide, I think there was written 0.1 gigaparsec, but I think you said 0.1 parsec. Is that correct?
It's 0.1 gigaparsec, so 100 megaparsec.
All right, and no, sorry, I got that wrong, definitely. So what is the distance of the 10 solar mass black hole from the 10 to the 6 solar mass supermassive?
You mean
year from 1 year from merging, right? What
yes.
I mean,
Okay, I don't remember how far the small black hole is from the big black hole, because this we use a waveform model which do not use, let's say, physical measurements. But this is an MRI which ends in a plunge. So it starts 1 year before plunge. It runs for a year and then it falls in.
All right, thank you.
Thanks. I see Shane has a question online.
Yeah, thanks, Alejandro. This is cool. So the thing about this that I can't quite fathom from what you've told us is this corner plot especially shows the effect of the kind of velocity relative to the detector. I guess what I'm wondering is, for you to understand the bias this puts on the parameters you're showing, you need some way of measuring the velocity itself. So is it possible to disentangle the velocity from this, or do you need the velocity by some other method in order to correctly interpret the parameters of the source?
Okay, this is something which is still under debate. My current understanding is that we can detect the velocity, because the idea that we cannot detect the velocity basically comes from this idea of mass redshift degeneracy, right? Like that we could just change the source. However, I have here a small graphic on this. Like, the idea of mass redshift degeneracy is basically saying, okay, we have some source which by cosmological expansion just appears bigger. So there is like a global rescaling of the time, of the mass and the scale and the length scales. All this can be made bigger, and therefore there is this confusion if the source is indeed bigger or not. However, for Lorentz transformation, we have a preferred direction of the transformation. So like shown in this picture, a circle does not transform in a bigger circle, it transforms in an ellipse, which you could, for example, imagine for your orbit. A circular orbit doesn't look like a circular orbit when the source is actually moving. So my understanding is that the mass redshift degeneracy does not exist for motion, at least not if you really consider all modes, because for one singular mode, you can still readjust everything. But when you start comparing the different modes, then you see it's similar like for light, when you have like the atoms and you only see one line, you don't know if it's redshifted. But if you understand that they are like getting bigger the distance, you get that your source must be redshifted or something like that. So my current, I think personally that this can be detected alone from gravitational waves. And which I think makes it particularly interesting, but I'm still working like on a definite proof to make that, because there are still doubts from different people.
Okay, this is interesting. I'll think about it. I'll probably chat with you some more about that. This was cool. Thank you.
Thanks. You're welcome.
Great, thank you very much, Alejandro, for a very interesting talk. So I think we'll move on now to Alexi's talk.
Thanks again, everyone.
Alexi, can you share your screen?
Sure thing. Hello.
So yes, Alexi will speak about black hole binaries in globular clusters are shaped by gas. Please go ahead.
Pleasure to be here, and hello.
Your audio is a little laggy, I think.
Okay. Can you hear me? Yes.
So it comes in and out a little bit, so we can't hear you very clearly.
Very well.
That's only better.
Okay, perfect.
No.
Oh no, it's gone again. Yeah, it might be worth turning off your video to see if that helps.
So this is my second backup internet.
That sounds better.
Yes.
Okay, no, that's optimistic. All right, so to the business then. Binary black holes in the global clusters are shaped by gas. That's what I want you to remember from this talk. So this is the key points I want you to remember. So I'll try to follow through a sequence of statements that are hard to argue against, and here they come. Well, we see black holes in LIGO data. Here's a plot from Maya Fischbach paper, and here on the plot we see the distribution of masses of LIGO black holes. And the green curve shows the masses of the black holes, which are inferred if you account for the biases, for the fact that we are easier observing the black holes of higher masses. So, when we look at this curve, we see that there are bumps and irregularities, and one might argue that the data contains more than one population. So the statement which is very hard to argue against is that probably there is more than one population that is observed in LIGO data right now. And it actually matters very much for LISA, as for example, as we heard from Alejandro just before me, if black holes are made, for example, in some unusual environments, for example, in AGN disks or in triples or in some other environments, we might well pick up the signatures of that in the. So second, in global cluster, global clusters, and X-rays. And in X-rays, we see quite many X-ray sources centered inside the cluster, and we see that there's quite many X-ray sources in 47 TAC. And generally speaking, maybe not all of them contain black holes, but quite a significant fraction of them could be containing black holes. And secondly, we also know from evolutionary reasoning that if star produces a black hole, probably doesn't receive a very big kick, and so there are good reasons to believe that there's quite a good fraction of black holes which are retained in global clusters because they don't receive such large kicks to escape the cluster. And finally, black holes are have even yet more reasons to believe that black holes are present in global clusters. So the question perhaps really is whether the black holes in global clusters can become LISA sources. And to answer that question, we have to model global clusters. And to model global clusters, there's quite many things to consider, and I will just list some of them pretty briefly. So first of all, if you think about how to make black hole binaries which are merging inside global clusters, we have to think about single and binary stellar evolution because stars evolve in clusters. On top of that, stars sometimes form triples and quadruples, so we have to think about how quadruples act in global clusters that has not yet been fully explored so far. On top of that, the stars in clusters can collide physically, for example, and form merged objects. And yet on top of that, stars in clusters, sometimes, for example, singles and binaries in clusters can encounter each other and also produce outcomes of encounters. For example, you could have two stars encountering one other star, and In that case, for example, one star might exchange into the binary, and for example, one other star might be lost. So there are diverse outcomes of encounters of binaries and singles in globular clusters. And yet on top of that, there's also structural evolution of the whole cluster. So the cluster might evolve over its lifetime. So therefore, this whole picture of how black hole binaries are formed has to be considered by thinking about all these effects at the same time. And the thing that I want to point out is that actually there's one more player in the game, and namely that is gas. So gas actually can also have effects on, quite significant effects on black hole binary population in globular clusters. If we include gas, the globular cluster could look very differently. So without gas, like present day, all globular clusters look like here, but if we include gas, they might have looked like here. And the point is that right now on the picture, we're looking at a young star forming region, the trapezium cluster. Its mass is quite significantly smaller than the mass of typical globular clusters, but still its appearance is possibly representative of the very first years of globular clusters, for example. And in fact, when we have gas in globular clusters, there are quite several things that could matter. And I'll try to first, before I go into these things, I'll try to convince you or explain at which stages do we expect the gas to be present in globular clusters. So first of all, it's again very hard to argue, but the stars form from gas. And when the stars form from gas, there's still some gas around. So some gas around might still act on some of the stars which are just forming. So it's not an instantaneous process. So there might be stars interacting with gas in the first 10 megayears of globular clusters, for example. Also, some observations of young massive clusters, particularly young ones below 10 megayears, also show signatures of gas. Perhaps a stronger evidence for gas in globular clusters is that in globular clusters, we see multiple stellar populations. The stars in globular clusters seem to have undergone some significant transformation so that half of the stars have ages inferred from present day observations, which are a few hundred megayears different from the ages of the other half of the stars. In other words, people believe that there was some significant effect acting in some ways on about half of the globular cluster stars over time scale of about 100 megayears, give or take. And on top of that, one might think about different other effects which are considered in models. For example, the AGP stars have winds which might be retained in globular clusters. So for example, there are gas inflows which might end up in globular clusters. And these effects happen on timescales of 50 megayears or so. And when gas ends, or when the gas enters the globular clusters, it can do quite many things. So first of all, if you have two stars flying around and there's gas around them, for suitable relative velocities, the stars can form binaries. That actually is an active process. So binaries may form in the gas. This process is quite similar to what is observed in or what is modeled in AGN disks. So people also believe that binaries can form through the gas friction. On top of that, if there is gas and there are stars, for example, binaries encountering binaries, so binaries encountering singles, then the gas can enhance few body interactions, as in the number of strong interactions might be different, might be higher. Further on, the gas might make binaries spiral in, and I'll show examples of that further. And finally, the gas, if the stars are in gas, they might accrete that gas and grow. And that affects both stars and black holes. So here's a plot from the paper by Moore, Rosner, and Hagai Perez this year. And it shows what happens if there is a binary 10 plus 10 solar mass black hole in a globular cluster of a typical size, about 10 to 6 solar masses. And if the globular cluster contained 3 10 to the 5 solar masses of gas, that was decaying over time scale of about 50 megayears exponentially. And what we see basically is that the black holes can spiral in for different initial pericenter separations between 1 AU and 0.2 AU over a very short time scale of order of 1 megayear and maybe a few tens of megayears. And this happens pretty much because the eccentricity of the stars is increasing by the gas. So the overall picture is that when the stars reach the upper center, the gas friction is at its highest, and that makes the stars spiral in or kind of become more eccentric, particularly effectively. Now, that certainly can matter a lot for the black hole population, because the black hole binaries in globular clusters might merge very early on due to the presence of gas, or they might also merge when the gas is flowing into the globular cluster. The next effect is, I want to to discuss is the Bondi-Hoyle accretion. So if there are stars in an environment, on a gaseous environment, they are going to be accreting mass due to Bondi-Hoyle accretion. This is the equation. I think the key points from the equation are that the accretion is quite a strong function of mass. So the more massive objects accrete the best. It's linearly proportional to the density of the gas. And I have put it in numerical form with the most typical parameters for global cluster gas densities and for speed of sound, which is very typical for global cluster, if not conservative, and the mass of the 20 solar mass black hole. So, and from this equation, we can see that a black hole can accrete in a typical gaseous environment about 16 solar masses in about 100 mega years. So, and I remind you that multiple populations in global clusters show evidence for gas acting on timescales of few hundred mega years, potentially. So that means that black holes potentially can accrete quite significant amount of mass. So we do a simple experiment like this. So we set up a collection of stars, which have binned. In the collection of stars, the stars follow the tracks from detailed stellar evolution called MESA. It's called MIST. So the stars evolve in a configuration like we see in the picture. There's gas on top of the stars, and the gas is injected at 200 mega years into the cluster, which is representative of the age of multiple populations. And we choose relatively conservative properties of the gas and the speed of sound. And we account for accretion, and we account, so there are no binaries in here, and we only trace the number of, trace the mass of the neutron stars and black holes. And basically what we get is that, well, these are the growth tracks of neutron stars and black holes in that simple setup. So until about 200 mega years, the masses of neutron stars and black holes were constant, nothing was constant. But once the gas was injected into the cluster in a small amount, it was only 10% of the cluster mass or so, the gas has led to the growth of the black holes quite significant amounts. And likewise, the neutron stars have also increased in mass to the masses beyond the neutron star collapse into black holes. So I guess the point is that the gas can change quite much the properties of both the binary black holes, but also of the masses of black holes. This exact evolution that we see here, perhaps maybe is not yet complete. So it's part of the paper in prep. So there in particular, probably the effects of feedback that limit the gas. I should mention that this growth is sub-evident because black holes are allowed to accrete that much mass, but their accretion might also make feedback or produce feedback on the gas in the cluster, which might change the overall gas density, and therefore maybe could limit the accretion. So that potentially is a limiter. But also a prediction of this scenario is that probably in the global clusters, if black holes have been affected by gas, there should be also a population of either high mass neutron stars or low mass black holes. So in other words, black holes which are in the mass gap. Then just a quick note that actually, you know, if there is a gas injected in global clusters and black holes are affected, then also other populations are affected. For example, white dwarf populations are affected. And in fact, this is good because, so here on the plot, we see the masses of white dwarfs and the number of white dwarfs, and the colors both show the population of white dwarfs every shifted by 25 mega years. And so we see that that initially the population of white dwarfs would be described by the black line, and that over time the white dwarf population shifts in mass, and some of the white dwarfs shift in mass beyond 1.5 solar masses. So which means that some of the white dwarfs experience accretion-induced collapse into neutron stars, which is actually pretty good. So I will not go very much into that, but it's the subject of the paper by Hagai Peretz. And the point is that in global clusters, there's this so-called neutron star retention problem, where people say that it's very hard to produce the population of neutron stars observed in global clusters by single or binary stellar evolution alone, because the neutron stars get kicked out of global clusters very effectively. But in this scenario, if white dwarfs accrete mass from the gas, they can actually become neutron stars through accretion-induced collapse, and they don't get kicked out. So that means that the neutron stars are present in global clusters, in fact, in reasonable numbers compatible with observations. And even a bonus on that, so if there are neutron stars produced through this scenario, the gas spins up the neutron stars and turns them into millisecond pulsars, which is also the state of neutron stars that we see them in the global clusters. In other words, it kind of solves several problems at once. So summary comes here. So first of all, I mean, the key point and the thing I want you to remember is the title. So basically, gas shapes the black hole population in global clusters. The effects of that could be diverse, but the potential is quite significant. So the presence of gas might affect the black hole mass distribution. It might affect the properties of black holes we observe in LISA. It might also at the same time solve the neutron star retention problem, and potentially could explain the wide dwarf population and affect the populations of other stars. And finally, I should mention that this research is supported by this next project in Hagai Ferris group. Thank you so much. Okay, got it. So if there's no audio from the room, I suppose that we should switch to text. Well, okay. So there's a question which states, is the accretion spherically symmetric? And I can say that the accretion is not exactly spherically symmetric. So the Bondi-Hoyle accretion works as follows. So when there is a star in the gas environment, the star deflects the gas that flows towards the star, and some of that gas gets trapped because it's gravitationally focused and forms some of a amount of gas behind the star. So in other words, the star finds itself surrounded by the gas of low velocity dispersion somewhat centered on the back of the star, and then it accretes onto the star. So it's not perfectly spherically symmetric.
Wait, can I ask, can you hear us now?
Yes, I can hear you.
Okay, good.
So
Would you like to say?
yes, let me repeat my question. So are there any observational evidence that massive clusters, progenitors of globular clusters, can retain gas at the ages that you're describing? Because my understanding is that there is no observation of a massive cluster with gas past 2 million.
Yeah, so that is quite correct. Can you hear well? Yeah, so that is correct. So we do not see the clusters which are retaining gas at the present day, but it also should be remembered that present day we see the clusters which are really old, 10 gigayears old, and at least 2 gigayears old.
Talking about young massive clusters in extragalactic.
We do not see young extragalactic clusters that contain gas that we can recognize as global clusters, but we see star-forming regions with lots of stars embedded in significant amounts of gas. So in principle, we do not have yet claimed direct detection of gaseous global cluster, but again, the point perhaps is that it will look very different from a typical globular cluster. So for example, if you calculate the gas opacity from a gas that can do things, the opacity does not have to be significant. But also, alternatively, the gas opacity could also be quite large, so that it's actually not recognized as a cluster.
Okay, thank you.
I see a question from Valeria, if I'm not.
Yeah, hi. Yeah, you mentioned effects for LISA. What could be such an effect on the population for LISA of this gas?
So, I mean, the main point is perhaps that the whole population of black holes in global clusters might be significantly modified. So, I mean, all the predictions of global cluster, or sorry, of black hole populations in global clusters should be potentially reconsidered with possible effects of the gas. So the effect of the LISA will be that it will be measuring different distributions of black holes. But I mean, at the present day, because at the present day there are no black hole binaries, perhaps it's a bit hard to say. I mean, so from the plot that I showed from Moore-Rosner paper, the indication is that the black holes are driven towards the spiral by gaining significant eccentricity. So potentially that could be retained, maybe. But that's so far that we can say.
Okay.
Do you want to?
No, it's fine. You can leave me.
Okay, and Valerie also has a question in the chat, but in the interest of time, we probably should move to the next speaker, which is Alberto.
All right. Thank you so much.
But thank you again. Okay, so Alberto will talk about massive black hole binaries, LISA, multi-messenger prospects, and standard sirens. Please go ahead.
So hi everybody, I'm Alberto Mangiardi, postdoc at the Laboratory of Astroparticle Cosmology. And today I'm going to talk about multi-messenger prospect with massive black hole binaries and about the type of cosmology that we can do with this type of sources. I will focus a bit more on the astrophysical side. I will present the model that we have for the electromagnetic counterpart, the number of counterpart, and at the end there is just a last slide about some preliminary results about cosmology. No, it does not. So okay, I guess that we're all familiar with the black hole mass spectrum. We are all familiar with the black hole mass spectrum. So we have stellar black hole, let's say from 5 to 100 solar masses, that's like we is currently observing binaries. And then we have massive black hole from 10 to the 5 to 10 to the 10 solar masses that we think they reside at the center of galaxies. So the idea is when two galaxies merge, also the massive black hole that is the center form a binary and eventually merge, emitting gravitational wave. And as we all know, in mid-2030s, LISA is going to observe the gravitational wave from these massive black hole binaries. And here on the bottom right, you can see the typical signal-to-noise ratio that we expect for this type of sources. So you see that there is, you can see my cursor. You can see that there is a range of masses from 10 to the 4 to 10 to the 7 solar masses, where basically we can observe the population of emerging massive black hole binary in the entire universe. So why we want to focus on massive black hole binary? Well, first of all, from an astrophysical point of view, we want to understand how these binaries form and evolve. But we also expect these sources to be key sources for multi-messenger astrophysics because they might be surrounded by gaps. And at the end, gravitational wave carry the information about the luminosity distance. So, for example, if we get the redshift from an electromagnetic counterpart, we can do cosmology. So we started this project with the idea of upgrading some previous work done by Nicola Tamarini in collaboration in 2016. So the idea is to establish the number of counterparts that we expect over LISA time mission and check what type of cosmology we can do with this type of sources. So we performed two major improvements with respect to the previous work. So we improved the modeling of the electromagnetic counterpart, and we performed the parameter estimation of the gravitational wave signal with a by design code that has been developed by Silvan Massat. It's expensive because it's by design code, but it's actually close to the realistic scenario. I have no time to discuss about it, so I will just focus on the electromagnetic counterpart. So at a starting point, we need a population of merging massive black hole binaries. So we took the results of semiotical code developed by Enrico Barause. We have three main astrophysical modes, just to envelope our uncertainties. We have a light model where we have black hole of 10 to the 3 solar masses, a heavy model where black holes start already at 10 to the 4, 10 to the 6 solar masses, and then we have a heavy no delay model where we remove the, well, there is no delay between the galaxy merger and the massive black hole binary merger. We know that it is not, let's say, realistic, but just look at this model as an optimistic one because it provides more massive black hole binary mergers. Once we have the population of massive black hole binary, we clearly have to compute the electromagnetic counterpart. Again, as we have learned yesterday, we really don't know what type of electromagnetic counterpart we expect from this type of sources. So we just assume that we have electromagnetic counterpart in optical, radio, and X-ray. And clearly, once you have the different electromagnetic counterpart, you also have to combine this with a telescope that basically can observe this counterpart. So, for example, for optical, we choose the Vera Rubin Observatory. For radio, we have SKA, and for X-ray, we have, maybe I should say, we have Athena.
So the idea is that, for example, in optical, we have the ruby, so it has a field of view of 10 square degrees. In optical, for example, we can do both the identification and redshift. So we can identify the galaxy and get the redshift, because at the end we want to do cosmology. With radio and X-ray, well, in radio, for example, we have a field of view of 10 square degrees. Athena has a field of view of 0 square degrees. In radio and X-ray, we can identify the galaxy, and then we can get the redshift, for example, with ESP, for example. We also have two additional variations to the model. So we took into account the possibility of a gen obscuration. So we took into account the possibility that the same gas that is producing the electromagnetic counterpart is also absorbing a fraction of the luminosity. And this affects in particular the optical and the X-ray part. And for radio, we took into account the possibility of a collimated radio emission with an opening angle of 30 degrees. So just last technical slide. This is the model that we use for the radio emission and for the X-ray. So for radio, we are just assuming that the luminosity is a flare plus a jet, where the flare is just scaling roughly with Eddington luminosity, and the jet comes from this paper of Meyer in the 20s. For X-ray emission, we basically computed the volumetric luminosity, converted it in X-ray, and computed the fluxes. So this scheme summarizes more or less our procedure. So we start from the raw catalogs. So really the number of massive black hole binary merger in a given year. We first of all computed the detectability of the gravitational wave signal. So we selected only systems with SNR larger than 10. Then we computed the detectability of the electromagnetic counterpart. And we selected only systems that have a detectable electromagnetic counterpart. And in the end, for this system, we simulated the parameter estimation. Because at the end, what we want is the rates of the electromagnetic counterpart, that in our studies are basically defined as systems that have a detectable electromagnetic counterpart and that have a sky localization which is enough accurate to allow basically to detect the electromagnetic counterpart. We have two different models, maximizing one and minimizing one, in the sense that they maximize and minimize the number of sources that you expect. So in the maximizing one, we do not have obscuration. We assume an isotropic radio emission, and the X-ray emission comes assuming Eddington accretion. In the minimizing one, we have obscuration. We have the radio emission collimated with a jet of 30 degrees. And the X-ray emission comes from the amount of gas that we have from the semi-analytical model. So we can just start looking at the raw catalogs and apply all the different steps. So for example, here the dark blue dotted dashed line represents the raw catalog, and the bright blue solid line represents all the system with SNR larger than that. So you see that, for example, for the EV model, we are able to recover the entire catalog, but for the light model, we are basically missing a fraction of sources at low mass and high redshift. This is expected because the laser is not really sensitive in this mass region. If you apply the requirement on the detectability of the electromagnetic counterpart, in terms of redshift, we select all the system at redshift, let's say more or less less than 8. In terms of total mass, we select preferentially system at higher masses because they have typically more gas, so the electromagnetic counterpart is brighter. And at the end, we can apply the requirement on the sky localization, basically. And as you can see here, you can compare the dark green with the bright green line. We lose again a fraction of system. The reduction is significant, especially for light model, because again, these systems are let's say light, so the parameter estimation is not so accurate for this type of system. I mean, the sky localization is not so great for this type of system. And in terms of the electromagnetic counterpart, we can also look at the magnitude and the fluxes that we expect for this type of sources. So, for example, here in top left, you see the magnitude that we expect in optical. Well, as you can see, you can already see from the y-axis that we do not expect many sources. But also you can see that when we include obscuration, basically the number of counterparts drastically decrease. Bottom left, there is the flux that we expect in X-ray. And again, as we go to lower fluxes, we have more sources. And on the right, there is the fluxes in radio, in the isotropic, or in the case where we take the opening angle. And again, you see a reduction. So bottom line of this slide is that overall, we expect a few and fail sources for massive black binary for real. And indeed, we can just look at the number. So let's just focus on the heavy model for simplicity. So for example, for LSST in Fourier, we have 4 counterparts. However, if you include obscuration, the number goes below 1. For radio, for example, we expect 15 counterparts if the emission is isotropic. But if you assume a jet, basically we just have 3 counterparts. Similarly, for Tina, we expect 3-4 counterparts in Fourier if there is no obscuration. With obscuration, we again go below 1. So in this table here, instead, we just summarize the number of counterparts if we combine all the different strategies. But again, just focus on the heavy model. Overall, we expect 15 counterparts in Fourier, and in the minimizing model, we expect 4 counterparts.
5 minutes.
Yeah. So just some preliminary results about the cosmological application, because the idea at the end is what we want to do. Well, you can see here that, for example, we are able to constrain H0 at 4% in this case. This has been done with the maximizing model, so we have something like 14 counterparts. I would say that at the end, taking into account that we also have the minimizing model where we have less counterparts, at the end, probably the error on H will be around 10% with this technique. So conclusion. My conclusion is that massive multi-messenger and cosmology with massive black hole binary is going to be challenging. Currently, the peak of the distribution is around redshift 2, and the massive black hole binary that we expect are not particularly bright because they are masses around 10 to the 5, 10 to the 6 solar masses. So we need to accurately plan any follow-up strategies in order to maximize the number of counterparts that we can possibly detect. About cosmology, again, at the end, probably we will be able to constrain H0 at 10%. But the idea is that clearly, okay, LISA will not observe just massive black hole binary. In principle, LISA will observe also stellar black hole binary and extreme mass ratio spiral. So the idea, is still in preparation, but the idea is that clearly we can want to combine all the different, all these different sources and basically construct a sort of a cosmic ladder in terms of gravitational waves, where we have stellar and then at low redshift and massive black hole binary at redshift 2 or 3. So thanks for your attention, and I'm happy to take
Questions, Chris?
Thank you. I think it was on your plot, but it just went too fast for me to pick it up. So this 10% measurement of H0 coming from a handful of massive black hole binaries. How many binaries and at what redshift are they?
Okay, this model, this maximizing, we have something like 10 standard size and 10 counterparts.
But over what range of redshifts?
Redshift 2 or 3. This is the peak of the distribution, basically. You can,
yeah, it was in these plots, but I just wasn't fast enough to pick it up. Yeah.
Well, okay, you can go also at redshift 4 or before.
So that's an interesting range for cosmos. So the absolute error on H0 is a bit pessimistic, perhaps, but the range of redshifts over which it's measured is very interesting. Yeah, thank you.
Okay. Maybe I missed that, but can you say a bit more about how do you get actually to the magnitude? Like you showed that this is the magnitude you expect. Is that the quiescent magnitude of the galaxy, or is that?
No, I mean for optical, we are assuming that there is an AGN. Oh, so we are assuming that at some point, optical electromagnetic counterpart is triggered by event.
So if you have no transient event, how many galaxies do you have in an error circle, and how hard is it? Because that would be challenging if you have like hundreds of galaxies and there's no transient event. How do you know it's that galaxy in particular? Okay.
I do not have a question.
Okay, no, that's fine. I just that's not my field, but it's really interesting. Okay, I see.
I mean, basically here we are assuming that there is a sort of rebrightening. So maybe you can say that maybe we stop in the sky and we compare. I mean, for example, here I included also as SST. So the idea is maybe we can use an SST. We look at current data and this also was already present.
Okay.
But still, yes, it's a bit different.
Cool. No,
And also, if I can add, this is something that's being looked at. How how big your sky error is, and I don't think we have a clear answer yet, because higher modes will make the signals longer, so you want to constrain your sky area better, but they're also going to be more quiet, so how?
I see.
So it's an interesting question.
No, that's a good project.
I have a very simple question. So you finished a little bit on a pessimistic note that it will be challenging, and I wanted to turn it on the optimistic note. So what if we are lucky? What would be like the luckiest possible multi-messenger observation?
10 to the 5 at redshift 0.5. Because for that you have already a good sky localization during the spiral. And for that, maybe if you are really lucky, you can get something from it. But you have really to do.
From the like EM point of view, like how it would look like, what are the patterns?
Remember that we did this 10 to the 5 at redshift 0.5 for Athena, because we were assuming an X-ray counterpart. I have to check honestly for optical array. But the point is that, okay, if it is so close, I mean, we will point everything, I would say, because this identification would be incredibly strong.
Thank you then.
Sorry, may I ask a question to Alberto?
Yeah, go, Federico.
Oh, yeah, so just the speaker sets up. Go ahead.
Okay, I just wanted to ask, I missed the point, because I was wondering, since Alberto in his last slide mentioned follow-up strategies, I was wondering if he expected different time delays between the gravitational detection and the electromagnetic one. I mean, for example, if we had a jet emerging from the remnant black hole after coalescence, we would expect that it propagated for almost undisturbed for a certain time t, then it would decelerate because of room pressure, and then emit because of shocks. And did you consider the time delay between the two events?
No, we just assume that basically if for example, in the radio, if the flux is enough to be detected, we detect it. So there is no difference between the merger of the massive black hole binary and the production of the electromagnetic counterpart. But clearly, I mean, you are right. It is another source of uncertainties, basically.
Okay. Thank you very much.
Okay, thank you. So the next speaker is Eliza. We will talk about gas stars, gravitational waves on the main line.
So, thank you very much. Okay, so today I'm very happy to be here. I'm going to present work that has been done in collaboration with Alessia Planchini, Matteo Bonetti, and Alberto Susana that focuses actually on the path to coalescence of massive black hole binaries. So yesterday you already have seen this plot. All the phases that massive black hole pair has to go in order to reach the final coalescence. In this talk, I'm going to focus on the small scale evolution. So when the binary is already bound. And I'm going to present a project in which we try to take into account multiple effects that can act at the same time and affect the binary evolution down to its final coalescence. And in particular, I'm going to talk about the stellar Bevel hardening, the effect of gas, and of course, gravitational wave emission. And why this? Well, because actually most studies that try to model this last bit of the spiral only assume either the galaxy host to be purely made of stars or just to be a disk of gas, basically. But in fact, we know that most of LISA hosts are going to be very rich in gas and also have their prominent stellar population. So it's very important to take into account both. So let's go a little bit more into detail on the projects that shrink the binary. So when the binary is bound, the stellar-driven hardening happens in this way. A star gets close to the binary, it interacts with it multiple times, and eventually it gains positive energy, it escapes the galaxy center, and the binary shrinks further and further for every stellar interaction. Of course, we very well, of course, if there is gas in there, also it can have an impact. Actually, initial studies suggested that gas could help ferrying the binary down to the gravitational wave emission stage, but the recent studies suggest instead that depending on the configuration of the disk and the binary properties, actually the binary cannot just shrink due to the gas evolution, but in some situations also expand, especially if the binary mass ratio is reasonably close to 1. So this is, of course, something that we really care about, because if this would, could in principle mean that some binaries would never enter the LISA band just because gas prevents their shrinking. Of course, if at some point this doesn't work anymore, or it doesn't work, we will have gravitational waves in the last bit really driving the final coalescence. So what we did here is to model those three processes in a semi-analytical fashion and put them together in order to really understand when gas-driven expansion can prevent our binary to merge. The stellar-driven hardening, the evolution of the binary semi-major axis as the derivative of the binary semi-major axis in time scales as minus a squared, which means that as the binary shrinks, the efficiency of this effect gets smaller. This is actually a very solid, it's a well-known relation concerning the stellar-driven hardening. Also, we very well know from Peter's papers that the gravitational wave in spiral scales as minus the semi-major axis to the -3, meaning that it sort of run away. Once gravitational waves get efficient enough, you cannot really escape from there. And then we have this gas-driven evolution. If we very pessimistically assume that gas can only expand our binary, then the scaling that was derived in this specific paper, but it is in agreement with many others, the binary expansion scales as the binary semi-major axis. And of course, whether the gas-driven expansion occurs or not really depends on the normalization of this curve, which is this number here, relative to the gravitational wave and the stellar-driven hardening. In particular, the gas-driven evolution scales as the m dot, which is the binary mass accretion rate, divided by the binary mass. Okay, so of course, in order to properly model the accretion, we have to make assumptions for it, because you can assume your binary accretes in very different ways. We explored actually different situations. We found that the worst case scenario is assuming that the binary always accretes at a fixed Eddington ratio. So at a fixed fraction of the Eddington limit, basically. And we call this Eddington ratio with this letter F-Ed. And we play a little bit with this number. Already by plugging in the equations I showed you before with these simple assumptions for the mass accretion, we were able to say that gas-driven expansion can only occur if the binary accretes significantly. And depending on the binary mass, the minimum accretion Eddington ratio for the binary to have some expansion goes from nearly 10% to 50%, meaning that really this binary needs to, be embedded in a very gas-rich environment. And also another important point is, can the binary expand forever? Of course not. At some point, it will even, I mean, it cannot reach a megaparsec with this mechanism, right? And in particular, we decided to stop the expansion, if it ever occurs, at the binary self-gravitating radius, which is the radius above which the structure of the disk starts developing structures, can start fragmenting and so forth, so that there is no evidence for the binary to expand anymore in this regime. And in particular, this is the scaling of the self-gravitating radius depending on the Eddington ratio and the binary mass. And actually, by also assuming this limit for the expansion, we were able to derive the fact that the gas expansion cannot work if the binary mass is above 10 to the 8-ish, because basically the disk is always in the self-gravitating regime at all the relevant scales for this process. Okay, but now let's go a little bit more into the evolution. So we put everything together. We evolved the differential equations for the binary semi-major axis and mass accretion, and we derived the evolutionary graphs. So now I'm going to show you the evolution of a 10 to the 4 solar masses binary, which is very small actually, but just because this small mass is what maximizes, so the worst case scenario that maximizes the gas-driven expansion. What you are going to see here is the binary semi-major axis as the function of time, the binary mass as a function of time, the binary residence time, which is a proxy of how much time the binary spends at each different separation as a function of the binary semi-major axis, and the binary mass as a function of the binary semi-major axis. In particular, in gray here, you see the case in which the binary doesn't accrete, so there is no gas. Of course, as we expect, only stars play a role, then gravitational waves, everything works very smoothly, the binary mass remains the same, and the binary merges relatively easily. If we start putting Eddington ratio, which is 0.6, we see that the binary evolution is this blue curve. So the binary in spiral is delayed, the mass grows a little bit, but still we have no expansion. Instead, if we put the binary Eddington ratio at 1, the binary shrinks for stars a little bit, then it hits gas stars becoming dominant. The binary expands, it hits the self-gravitating radius, it basically stalls there. But while stalling, the binary mass continues growing. And this means that at some point its mass is so large that the gravitational waves at this specific scale are strong enough to drive final coalescence. And I want to mention also that if we put the binary Eddington ratio even larger, the evolution is pretty much the same, but everything happens faster. So it's not that the binary takes longer to spiral as we grow this number. And also I want to mention that in the expansion cases, the binary mass grows so large that in fact it will go from the LISA band and enter basically the band of detection of pulsar timing arrays. Yes. Okay, thank you. And here what I'm showing you is depending on the assumed initial binary mass, the time scale the binary takes to reach the final coalescence as a function of what we assume to be the Eddington ratio. And what we see is that if the Eddington ratio is too low, is the same result as not having gas there. Then basically all our models have a maximum in spiral time scale close to Eddington ratio equal to 1, which is the first moment in which you can have gas to start playing a role. And above this value, then the spiral time shrinks again. And anyways, if you look at the time scales, so the spread for each given mass, gas-driven expansion cannot really lengthen the spiral by more than a factor of 10, more or less. And this is an important result because it means that this fact is not going to prevent our binaries to merge. So we are happy about that. We are even more happy because it would, in principle, also mean that they can stay for a longer time in a regime for which they can be really targeted by electromagnetic surveys and observed. So here is my last slide. The doggy bag for you to bring home is that we need to consider both gas and stars to live together in the galaxy and influence the binary evolution. Even if gas can expand the binary in some configurations, this does not dramatically impact the final time scale for coalescence, and so probably also the event rates we expect from LISA. And also binaries initially in the LISA band, if they expand, may enter the PTA band. And finally, this gas-driven expansion in principle can enhance our chances to detect binary candidates in galaxies electromagnetically. So I stop here and thank you so much.
Thank you very much. Do we have, yeah?
Can you please go to your plot, the one where you showed the other one? Yes, this one. So it's not clear to me, because if I understand well, you showed that the expansion is actually similar for higher fraction of the, for higher factor F, because we have that for the orange one is higher than for the green one. And it's not clear to me why it's not the opposite.
Here you have you have different processes. So in principle, if you have a Eddington fraction that is larger, you expect that the expansion would be more prominent, right? So the expansion is more efficient. And this just means that it takes less time for the binary to stall at the self-gravitating radius. So it will go up here faster, if it makes sense. And also, at the same time, it will reach in a smaller time scale the critical mass for which gravitational waves just drive coalescence. So it is true that gas-driven expansion is more important, but this just plays against it because then everything happens faster and we have the merger occurring earlier. I don't know if this...
So basically it's too fast and it cannot expand as much as with
it expands basically the same way, just the self-gravitating radius changes depending on the binary mass.
In this case, the binary mass is...
the initial binary mass, but you see here the mass skyrockets really. So also the self-gravitating radius works with that.
Okay.
So I have a rather naive question about why accretion necessarily expands the binary. What are exactly the assumptions we are making about the angular momentum that is ending up in the orbit?
Okay, yeah, so this is not really my main topic, but I think there is a lot of debate going on in the disks community of whether the presence of gas expands or shrinks the binary. It's not clear at all. Depending on the parameters you put there, you get different results. But now there is at least some consensus growing that because everything depends on the torques of the gaseous structure on the binary. And depending on whether the torques are positive or negative, you have a shrinking or expansion. And the sign of those torques are unclear, especially when you carve a cavity and then you have those mini disks around the binary. The torque by the mini disks and the overall torques are very hard to compute, very hard to simulate. And it seems that in some situations, the torques can be positive.
In the specific case, what did you assume? So there you're calculating somehow an expansion rate, right?
Yeah,
this is based on what assumption?
So basically, this was a work by Diego Munoz that basically derived these formula for the rate at which the binary expands. The disk here is relatively thick, and of course there are other assumptions in the initial parameters. But yeah, this is just a result from a simulation.
Okay, I think so. Marta has a question online. So if it's a quick question, maybe we could go
I
to,
will put it. I will add my question on the Padlet so that we save time.
Okay, thank you, Marta.
I have a quick question. To grow from 10⁶ solar masses to nanohertz type microbinaries, you have to accrete a lot of gas. So do you have to think about the typical duty cycle of AGN, or how much gas is even available?
Oh yeah, I mean, in principle, this was just the most pessimistic, just to make the binary expand as much as possible. But in fact, expansion can be stopped much earlier, just because the reservoir of gas is depleted. And in many of those situations, this would probably be the case. So this was just, to play the extreme case. But yeah, definitely.
Yeah, but if you ran out of gas, then you wouldn't be able to accrete to the masses that allow you to later in spiral. So
No, but if you deplete the gas.
Sorry, I think we might have to save this till later.
Okay, sure. I'm sorry. Yeah.
Yes, good. So the next speaker is Ricardo, and he will talk about the last 3 years multiband gravitational wave observations of stellar mass.
Okay. So thanks everyone. I hope you can hear me well from Zoom as well. So I'm Riccardo Buscicchio. I'm a postdoc here in Milan. I was a PhD here last year when I did this job together with many other collaborators that is listed there in some of the audience. Well, what we did was try to assess on a more robust basis possibility for a multi-band observation of stellar mass binary black holes, meaning once we'll have maybe third generation detectors or current detectors such as high sensitivity, what can we do together with LISA? And the idea is to simulate the entire signal across the band, and that's what we try to do. In the interest of time, I'll probably skip the introductory bit. I guess everyone knows what ET is probably going to be. LISA, the same, and second generation detector represents sensitivity. So let's go straight to the actual analysis. What you don't know is probably why our code that you see in the paper is called Barrow. I want to take the opportunity to say that now because so the reason is that Barrow, which is one of the characters of a Tolkien book, is being designed, inspired by the tower that's literally 100 meters from here, and that's the one you see. Now, joke aside, I wanted to mention that this analysis that we've developed is actually been applied to multiple sources, multiple classes of sources, and trying to make it as robust as possible. You let us slide with plenty of references if you want more about it. Now, the analysis, the important bit. So yes, what we did was to pick a few, well, 4 actually, reference sources in I can say a very limited set of sources, but still representative ones. And you can see, well, you can see here the characteristic frame for two sources. Yeah, you see the blue tracks and the red tracks are always associated with what we call light and heavy source, and they are actually labeled wrongly here because the blue is the light one. Yeah, so the reference masses that we pick are somewhat representative of I would say, an average detection in LIGO, as we've seen so far. So 40-ish solar masses for each component, 40 or 30. And for the early one, we had picked values very close to GW190521. So somewhat of a reference for what is lying at the end of the band for LIGO, at the end of the detection capabilities for LIGO. So you see the tracks there. You may be wondering why the signal is so loud in the ground-based detector, and the fact is that we adjusted the distance for those sources in order to have detectable signals in LISA. now the SNR in LISA is I think 14 for the heavy source and like 10 or something, around between 10 and 15, let's say. So it's a reference also trying to bracket the detection threshold for these kind of sources for LISA. You see some, I think, you see some peculiarities in this plot. First of all, you see on the left side, the I should point here, people on Zoom won't be able to see me. So you see on the left side of the plot, the signal being modulated, going up and down, both for the red and blue lines. That's basically LISA orbiting. So we have simulated 2.5 years of the mission. And then the signal basically goes blind in the network, respectively for a few days for the red track and for almost 2 weeks for the blue track. And then I think between 5 and 10 second signal long will appear in the ground-based detector. So yes, so as you can see, also we injected spins and we injected a few reference values for the eccentricity. That's why we actually used 4 sources. So the masses we used the same, but for the eccentricities we picked 2 different reference values, trying to understand what are the capabilities of them. And now let's start with the results. So the LISA results, which are, to me, are surprising, especially because I'm used to the LIGO standards for many of the parameters, and so seeing some results, it's very, very interesting. But let's focus on the important bits. So what you see here are the posteriors for the blue and the red source, and specifically focusing on some parameters which are interesting because of the multi-band interaction between the components of the network. You see in dotted lines the LISA posteriors with what I would say are very good posteriors on the chip mass and as good, well, very good, I would say as well, time to measure measurements, because we're talking about confining the time to measure down to a few minutes to hours. So it's extremely good. The important bit to keep in mind is the fact that since we can measure the eccentricity, and that can only be done in LISA, because we expect that to fade away once we get in the LIGO band, then we'll basically be able to break the degeneracies that are inherent when you only do the analysis on the ground. You see some arrows there pointing to some updated values, and those are basically the values that you get once you get to the ground. So the measure on the right is the error there, 3 × 10⁻⁴ solar masses is the error that you get from the ground-based detector, or I should say more precisely from the joint posteriors that you get from both LISA and the ground-based detector ones. And then you have, and then as you can see, the time to measure accuracy once you get to third generation detectors becomes super accurate. Well, I probably should skip. Yes, I should skip to the LIGO results very quickly. Well, I said LIGO, actually, I said the ground-based detectors results. Well, I would say probably, well, you can see very clearly the errors on the masses and on the spins are super good, meaning that we're basically we'll be able to pinpoint the values for the individual spins, at least for the magnitudes, and well, also for the misalignment on the spins. And so you can imagine these sources being described for their eccentricities with the LISA signal, and then we'll be able also to tell about the spins orientations once they get to the third generation detectors. And then, well, you can see from here the component masses. That's very important. The component masses will be pinpointed down, very accurate standards, and that's also due to the SNR that I was mentioning before, which is, I would say, super bright. That will open also a lot of questions on many other fronts. Let's keep them aside for the moment. And yes, so these are the individual results. I just wanted to mention a few, I think, important bits that might be relevant also for this meeting. So given that we have these observations, we can, in principle, for example, say with the LISA results, we can pinpoint the location to a given region in the sky. Do not take those individual numbers for granted. I'll say a few words at the end of the presentation. But ballpark, if we are talking about a few degrees squared, which is good standard, again, for GW standards. And of course, there are opportunities for doing follow-up searches for those sources, which some of you might be interested in. Similarly, one can, if one can point down the distance of the source, then we can do the usual distance and then figure out the possible association. We can figure out the constraints on the Apple expansion. So one thing I wanted to point out regarding this plot is that I put some multiple blocks. The reason being that the sky localization from the ground-based detectors, due to the, since we're basically playing with T, due to the degeneracies that are in the pipeline and therefore likely, cannot really distinguish some individual bits of the sky because of the localization and certain degeneracies. And so in principle, at least that's the way I see it. In principle, LISA, even if the individual localization is going to be poorer than the one from ground-based detectors, could be able to break the degeneracy and tell you which one of the plots are actually real one. And this is assuming that that multimodality stands there and there is no other way of breaking it. Smaller bit of improvement that, well, I shouldn't say small. It's an improvement that LISA will provide. And yes, so with those localizations, we've seen some numbers mentioned there in terms of hosts associations. And on the other side, given that we are capable of looking at these in spirals for quite a long time, we're talking also stay for a few years in band, we can in principle track down many cycles, and therefore you can test for the coherence with these signals with a possible type of radiation. Again, don't trust that number as it is, but it's a ballpark reference value. Yeah, so that's another opportunity. It's not going to be directly related to electromagnetic observations, but it's going to be, I would say, interesting results once we can place those constraints. I don't have a precise figure of merit to give you as a comparison for current constraints on the black hole charge. This is going to be competitive in 10 years from now or not. I can find it out if you're interested. No. 5 minutes. 5 minutes, okay. Yeah. Well, just wanted to mention something on the eccentricity because I skimmed over it. I told you we have 4 sources, and as you can see here, these are the posteriors on the eccentricity at the reference frequency, and the black line is the one that you get from the combined analysis after combining the results here with the ground-based ones. And you see in the upper row the high eccentricity sources. Right column, the heavy source, left column, the light source, and well, you can see that we can measure the eccentricity, especially for the I values that we pick in our table, while we can only place from the upper limits on if the eccentricity goes very, very low. Again, this is there is a caveat there. If you will look at the paper, you will see that so the value injected here is very close to 0. But we were effectively driving the posterior by the prior, therefore that should not be taken as a bias in the inference. It's a bias to the prior, so it's a bias. Yes, so that's really the last bit I wanted to tell you about the results from this analysis. It's interesting the fact that we can observe basically and recover the entire parameters, the entire sets of parameters. It's 17 parameters, yes, for these sources. And I think I'll thank you here for listening to me. If you have questions, well, of course, you can have a look at the paper. If you have questions, we have at least 4 times left, 4 minutes.
Thank you very much, Ricardo. Any questions from you? Yeah.
Just a quick question. You said if you moved your sources closer so that they're observable in LISA. Based on the current estimates for the merge rate density from LIGO, what would be the chance of observing a signal like this within 4 or 10 years?
At the sign sensitivity, which is the reference sensitivity that we used here, this
for LISA.
No. Well, of course, it was LISA the sign sensitivity, but we also used the sign sensitivity for the ground-based detector.
With ground-based detector, let's say that you have Einstein telescope,
Okay.
you can observe everything, but
Okay.
you put a black hole at a certain distance.
Yeah.
What is the probability of having a black hole emerge at this distance within 4 years?
I would say, I mean, in terms of number of detections, I would say a few.
Okay.
I don't think with third generation detector we can go beyond 10 something. But that's
If I can add. For the source that we brought most closer was the lighter one, so the one that's roughly the same as 16 and 914.
Yes.
And we brought it, I think, about 3 or 4 times closer than it actually was. Now we're seeing a few of those a year in.
4 times closer means that you decrease.
4 times closer than 15 and 914 actually was. So it was at 400 megaparsecs, and we brought it a few times closer.
Yeah, but that basically decreases the rate by 4
A
to the
factor of,
cube.
yeah, exactly. So, and we're seeing a few of those per year in LIGO at the moment. So the event is order one per LISA mission.
Yeah, but you see the heavier sources more easily in LISA, and they're harder to see in LIGO.
You're
So
talking about like
depends-
70, 80.
Yeah. So those sources are easier to see, and they're probably the most difficult to constrain with current ground-based detectors.
But the most rare also.
Yeah.
Intrinsically more rare.
Yes.
Yeah. But we have much less of a handle on the merger rate of 90 plus 90 solar mass black holes than we do on 30 plus 30.
Yeah, exactly.
So the uncertainty on the LISA merger rate is dominated by the high end of the spectrum.
Okay, so probably should move to the next speaker, but thank you again, Ricardo. So Nate, are you online?
Yes, hello.
Oh, yeah.
You able to see my screen?
Yep, we can see it well. So our next speaker is Nate, and he's going to talk about black hole spin alignment and disk breaking consequences for LISA.
Thank you very much, Anna. Can you hear me all right?
Yep. We can, we don't see the presenter view. We see like the view in the editor.
Sorry.
But you're coming through clear. Looks great.
Perfect. Okay. Thank you very much. I wish I could be there in person. I went to a workshop and I didn't even take off the name of that workshop off this slide. I'm sorry. Last week in Rome, and I got sick on my way back. So I really wish I could be there in person with y'all, but at least I got my voice back, so I can at least speak today. I'm going to talk with y'all about black hole spin alignment from the Barty-Pearson effect and the consequences for LISA. I'm a postdoc here at the University of Birmingham. I want to give a special thanks to Alberto Sassana and Massimo Dotti for very helpful discussions. And I do this work in collaboration with Davide Grossa as well at the University of Milano, Bicocca. So we're interested in talking about binary black holes. If you see BBH on the screen, just think binary black hole, please. They have an orbital separation, R, orbital angular momentum, L, and each hole has a spin angular momentum, S, which I'll probably talk about the dimensionless spin magnitude, chi, if I talk about spin. And so each hole also has a spin orbit misalignment angle, theta, which is really the topic of discussion in this presentation. And theta 1 just means the misalignment angle of the more massive black hole, and theta 2 is the misalignment of the less massive black hole. In general, supermassive binary black holes are thought to evolve in either gas-rich or gas-poor galactic hosts. That's kind of two umbrella classifications. And the great hope is that LISA may discriminate between these formation channels, hopefully by measuring the spin orientations. rather precisely. And as Lisa explained very in depth just before Ricardo, there's various processes that drive the in-spiral, the pairing and the in-spiral of these binaries over very large distance scales, as shown in this little plot here from Kelly et al. 2017. And the part of this in-spiral that we're going to be interested in today is this yellow region where the angular momentum loss of the binary is dominated by the viscous drag from disk migration when the binary is in a sufficiently gas-rich environment. And then we'll look a little bit at the gravitational wave emission phase as well at the end. So if we begin from the assumption that the binaries form with isotropically oriented spin directions, which is to say that there was no alignment process that was effective basically during the earlier phases, such as during the dynamical friction phase, then in the scenario where the binary evolves in a gas poor host, it's relatively well known that the initially isotropic spin directions will remain isotropic all the way through gravitational wave emission, which implies that the binaries will exhibit generic spin precession, which means that the orbital angular momentum will precess and nutate about the total angular momentum. But alternatively, in gas-rich hosts, the Bardeen-Pedersen effect can align the spins during this disk migration phase, but the amount of alignment that one would expect is highly uncertain due to the complicated disk physics and the physics of warped disk profiles. And so the model that we look at a system. We use a systematic approach to the Bardeen-Pedersen effect in circumbinary disk migration, which the Bardeen-Pedersen effect is essentially a combination of frame dragging and viscous interactions, where the inner region of each mini disk that forms around the black holes aligns more quickly to the black hole's equatorial plane than the outer region of the disk, which is working to align the black hole spin with the larger circumbinary disk on a longer time scale. That essentially creates a warped disk structure. And if the warp is sufficient and if it's helped along by perturbations from its companion, hydrodynamical simulations have shown over the last decade or so that the disk can actually break if the spin orientation is sufficiently near the orbital plane. As a simple kind of leading order result of this model, if we just assume that if the disk does break, we just hold the spin orientation constant for the remainder of the disk-driven in-spiral, then you get a picture that looks like this, where the left plot is for the more massive black hole and the right plot is for the less massive black hole. And taking an initially isotropic distribution of binary spin orientations, if the spins are initially sufficiently above the orbital plane, then the spins just get aligned rather efficiently and they remain aligned for the remainder of the in-spiral all the way through the gravitational wave emission dominated phase. If the spins are initialized sufficiently below the orbital plane, then they can experience alignment until they reach a critical angle, after which, for the remainder of the in-spiral, we just assume that the direction is constant through the remainder of that disk-driven in-spiral until we basically just turn on the gravitational wave emission, and that's why these lines start to oscillate up and down. But for some portion of this parameter space, some binaries can actually be initialized at a critical configuration, which basically is to say that the disk shouldn't really exist to begin with, and so that the spin orientation doesn't evolve really at all in this model during the disk migration phase. And so this happens for each black hole for its respective mini disk. And in this model of this systematic approach to the Bardeen-Pedersen effect, there's many initial parameters but you can kind of package them all together into two essential parameters that are dimensionless. So kappa governs the effect of the companion, and it's inversely proportional to separation. So it increases during as the binary inspirals. And essentially the initial kappa is going to determine if the binary begins at a critical configuration or not. And so the larger the initial kappa, the larger the parameter space, the region of the parameter space that the binary begins at a critical angle. And the other parameter is omega, which governs basically the relative contributions of the inspiral and alignment. And so if omega is larger, and that means that the Bardian-Pearson effect will align the spins faster relative to the inspiral. Generally, omega and kappa depend on the masses of the black holes differently. And so for each binary, you have 2 omegas and 2 kappas, which are necessarily unequal to each other. They'll only be equal in the equal mass limit. And this is helpful because this allows us to reduce the full parameter space down to 5 dimensionless parameters. Omega 1, kappa 1 for the primary, omega 2, kappa 2 for the secondary, and then the, the dimensionless viscosity parameter alpha, which is the usual Sunyaev-Shakura viscosity parameter. And so we can use these 5 parameters as kind of proxies and then relate them to the black hole masses and spins, which are the more physical parameters that Lisa will actually be able to measure. It turned out to be more helpful to look at the sum of the omegas, omega 1 plus omega 2, shown in the blue lines on this plot, and the ratio of the omegas, shown as the green lines in this plot, where these are contour lines as functions of the total mass of the binaries and the mass ratio of the binaries. And the orange and red lines are the initial kappas for the primary and secondary black holes. So just remember, omega is how fast does the alignment happen, and kappa is how strong is the effect of the companion, which can induce the critical angle. And essentially, for larger total mass, so as we go upwards in this plot, the initial kappas and the sum of the omegas are larger, implying that more binaries can reach the critical angle and they can align more quickly. And in the limit of equal masses going to the right side of this plot, the omegas become equal and the kappas become equal, implying that if the sum of the omegas is large, like greater than or approximately equal to 1, then both black holes will align quickly rather than just one of them aligning quickly. And it's worth saying that the initial kappa, the value, the kind of physical value of the initial kappas is usually not greater than 1, which actually coincides with the total mass of being about 10 to the 8 solar masses, which Lisa will have a hard time detecting binaries generally greater than that mass anyway.
5 minutes, Nate.
Thank you. And so for simplicity, to understand how the spin orientations evolve as a function of these various parameters, just for now in this plot, assume that the 2 initial kappas are equal and that the omegas are equal, and instead vary the value of the initial kappa in the columns and vary the value of the dimensionless viscosity in the rows, so that a larger smaller viscosity parameter means that the disk is less viscous and hence more prone to breaking. And like I said earlier, a larger kappa, an initial kappa, it means that the binary is more likely to start at a critical configuration. That's why in the top right corner of these plots, where each binary starts at a blue dot and evolves to a red circle through the disk migration phase, in the top right corner panel, there's basically no evolution of the spin orientations because they all start at a critical configuration. which is what the black box inside each panel shows. So that black box basically encompasses the binaries that start at a critical disk configuration. And larger initial kappa means that that black box gets larger. But as you increase the viscosity and going downwards on this plot to the panels on the bottom, you're able to actually have more binaries with their spins being aligned, depending on the initial value of kappa. And what this is one of the main results is that for binaries that evolve in gas-rich hosts with small alpha, they're basically, we would expect them to basically be indistinguishable from binaries that evolve in a gas-poor environment, because they're starting out, essentially most of them would be starting out in critical configurations, and so their spins don't really align that much at all. And next, now instead assume that alpha and kappa initial are fixed, and let's vary the ratio of omegas and the sum of the omegas to look at how the speed of the alignment changes. And in the very top row for a small omega sum, the alignment is very slow compared to the in spiral, and so not much alignment happens. But as you go downwards in the rows, you're increasing the sum of the omegas, and so the alignment happens quicker, and you can have very efficient alignments, which effectively creates different subpopulations of these binary black holes, depending on their spin orientations, as to whether or not either one or the other black hole gets aligned completely. Maybe so. Are you on the top right or the top the right border or the top border of the plot, or are both of the spins aligned and you're in the very top right corner of the plot? Or do both black hole spins reach a critical orientation and pile up on the edge of this black box? So you can have at most basically 4 subpopulations there, depending on the spin orientations. And just real quickly, it's possible that the ratio of the omegas in principle, in full generality, can be less than 1 or greater than 1, meaning that either the secondary or the primary aligns more quickly, respectively, which would result in basically either being having binaries pile up on horizontal lines or vertical lines in this plane. And I have a little animation that might be a little more helpful to show how the points actually move in this space. If you specify a total mass ratio, dimensional spin magnitudes, and viscosity parameter. I'll play it a few times, it's kind of fast. So moving from the blue crosses to the red circles, but we're watching the red circles move in time through the disk-driven in spiral. And this is for this choice of mass and mass ratio and spin magnitude. The omega of the secondary is larger than the omega of the primary, and so that's why the points move much more quickly upwards than they do to the right, because the secondary is aligning faster than the primary. But both omegas are greater than 1, and so both of the black holes are experiencing significant alignment. Like I said before, you can basically cut this into 4 subpopulations, as depending on whether both spins are aligned, only one spin is aligned, or both spins remain misaligned.
Hi, Nate, sorry to interrupt. We might have to wrap up sort of soonish.
Okay, yep, I got one more plot. I'm almost done. Basically, a significant fraction will still avoid misalignment, will still avoid alignments, which you'd expect them to experience generic spin precession, just like their counterparts would in a gas-poor environment. And I'll skip this plot and just go to the last one, where that was all disk migration stuff, but then of course the gravitational wave emission will take over, where in this plane, effectively, essentially the binaries will evolve on lines of constant chi effective, which is a post-Newtonian parameter that's conserved through the binary black hole in spiral, and which will slightly blur the position, the location of these binaries that avoid alignments. And this work will be published very soon, so please keep an eye out for it. And just to wrap up really quick, we would expect there to be a degeneracy between the spin orientations of binaries that evolve in gas-poor hosts and those that evolve in gas-rich hosts with low viscosity because of the existence of this critical obliquity. And if alpha is sufficiently high, then the Bardian-Pearson effect can align the spins to create subpopulations, depending on whether one or both spins are aligned. And we expect these subpopulations to exhibit different spin precession in the LISA band. And if LISA measures binary black holes with mostly aligned spins, and that would imply a formation in a high viscosity gas-rich environment. Thank you very much for listening. If there's any questions, I'll feel free to email me or contact me. Thank you.
Okay, yeah, thank you very much, Nate. So we might have to leave questions to we will contact you online or through Slack, I guess, also. But yeah, so we have a break now.
Yeah, so we have 10 minutes for the break, but maybe we can take coffee and biscuits in so that we allow the online speakers to start on time, and because of the time zones, and I mean, we cannot really get shift times, right? So sorry, apologies for that. For people on Zoom, this session will be closed and we will meet in the next one.